So the first thing that I want to talk about today is a review of sinusoidal signals. Goodness. So let's say that I have a sinusoidal signal, and I'm just going to call it X of t. I'm going to pre-apologize for being not particularly artistically inclined, but when it's important here in a couple of moments, we're going to switch over to Desmos graphing to help me out here. So I'm going to call this signal just X of t, where t is our independent variable. And let's say that I have the following signal. Okay. So something akin to this, where I can choose to express this signal, X of t, in one of two ways. I can either express it as a cosine function. So I'm going to have something like X sub m cosine omega t plus some phase angle theta. Or I could alternatively express this exact same signal as X of t is going to be xm sine omega t plus some phase angle phi. And the first thing that I want us to do is kind of unpack and make sure that we understand what all of the constituent parts of these sinusoidal signals represent, okay? So we're going to start with our amplitude. Okay. So the amplitude of a sinusoidal signal is the maximum value that the signal reaches in a single interval. Okay. So for us, this distance right here, measured from the horizontal axis to the peak, would be our amplitude xm. For what it's worth, the distance that we go from the peak to the minimum value is also going to be that exact same amplitude, okay? So this sinusoidal signal oscillates between, so it will have values ranging all the way from positive xm down to negative xm, depending on where we are at along that signal's repeated path, okay? Next, I want to talk about our angular frequency, okay? So our angular frequency has the symbol of omega. So this represents how quickly the signal is changing with respect to time. Okay. So it represents the speed of our sinusoidal oscillations. Now, this isn't something that we can directly measure from our graph, but it is something that we can get from things that we can directly measure from our graph, okay? So as a kind of a subnote thing here, let's say that our period T is defined as the amount of time it takes for a signal to complete one oscillation. Okay. So for us, that period would be something like this, okay? So we're starting at 0 at whatever point in time this is. We're ending at 0 at whatever point in time this is. So the distance between when our signal effectively starts over is our period t, okay? Well, our period t is related to the linear frequency of our signal, commonly denoted by the symbol f. And our linear frequency is simply the number of cycles that occur per, second. And it turns out that our linear frequency and our period are just inversely related to each other, because the period represents the total amount of time it takes for one cycle to complete. So we have time per cycle, and our linear frequency is just the flip side of that. That's the number of cycles per unit time. Okay. So we could say that our linear frequency f is simply equal to 1 over our period t. Well, our angular frequency and our linear frequency are related to each other, okay? Because we know that for each cycle, our sinusoidal signal undergoes a total angular change of 2 pi radians, okay? So we could say that our angular frequency omega is equal to 2 pi times our linear frequency f, which is the same thing as 2 pi divided by our period, capital T. So if we can tell what our period is, we can either get linear frequency or angular frequency. But we typically express sinusoids in this class in terms of their angular frequency omega. For what it's worth, our angular frequency omega is always measured in radians per second. And our linear frequency f is always measured in cycles per second, which is more commonly called the unit of a hertz, H-E-R-T-Z, okay? Bless you. So we've talked about XM, we've talked about omega. T is just the time that we're interested in. So the last thing that we have to talk about are our phase angles, okay? And this is probably one of the most confusing parts of this. So I have two different phase angles here, theta and phi, and I'm using those two different symbols to represent the same quantity, because looking at this graph with my level of expertise, I know that these two are going to have two different numerical values. Riel, did you have a question? They are the same thing. Well, actually, so a period is the amount of time it takes for one cycle to complete. So what a phase angle represents essentially is the amount of shifting away from the origin that the signal experiences. Okay. So let me explain what I mean by that if we go back and look at this terribly drawn diagram. Okay. So if we think about this signal that I've drawn in blue as a cosine function, what does the value of cosine of, let's just say, x have at t is equal to 0? What's cosine of 0? Or so cosine of x at x equal to 0. Sorry, I threw two variables at you like a jackass. It's early. But anyways, what's cosine of x for x is equal to 0? 1, right? So realistically, what we expect to have happen with the basic level of a cosine function is that it's going to hit its peak value at t is equal to 0. Okay. Well, we can see very easily that this guy hit its peak value at some time later than t is equal to 0. And our phase angle is representative of that time shift of our signal. Okay. So a baseline phase angle of 0 degrees means that it's behaving like a quote unquote normal cosine function, right? Now, what about a sine function, right? So a sine function, or what's the sine of 0? Let's just say that. 0, okay? So we can see that our sine function is 0 and increasing at some point less than t is equal to 0 because it's been shifted over to the left by some amount, okay? So we have some different phase angle representing that time shift to the left, okay? So generally speaking, we can say that positive phase angles represent a time shift to the left, okay? So we're shifting them to the left. So that means that they are beginning their cycle earlier than we would expect. So we would call this an advance, okay? And the amount of that advance, which I'm just going to call it delta t, is going to simply be equal to omega, that's radians per second, let me do it this way. Our phase angle phi would be equal to omega times delta t, or that delta t represents the amount of time shift that we've experienced. Okay. Negative phase angles represent a time shift to the right, which means we are delaying our signal because it's starting its cycle later than we expect. And in that case, our phase angle is going to look like just negative omega times delta t. Now, this may seem counterintuitive. A shift to the left is a positive phase angle, and a shift to the right is a negative phase angle. So just to prove to you guys that I'm not making this crap up, I want to take a quick look at Desmos, okay? So I've got a simple graphing program right here. So let's say that my first signal, y1 of t, excuse me, of x, is going to be equal to, let's say, 5 cosine 2x. And my second signal, y2 of x, is going to be 5 cosine 2x. And now I'm going to introduce some phase angle. So let's start with a positive phase angle. So let's just say plus 20 degrees, okay? So by default, this application is using radians as the default angle. So to do 20 degrees, I'm going to do 20 times pi over 180 to convert both of our angles into radians, okay? And we can see that our blue curve is shifted slightly to the left of our red curve. So it's advanced in time because it's hitting its peak value earlier, okay? If I change this phase angle to a minus sign, now my blue curve is shifted to the right, meaning that it's slightly delayed or it hits its peak value later in time. The larger that phase angle is, the more our signal is advanced or delayed, right? So right now I have a small delay, but if I did 200 degrees, now it's shifted out pretty aggressively to the right, so much so that it is well over half a cycle out of phase, meaning that we're seeing, positive peak on the red guy, and then we've got a pretty long delay until we see the positive peak on the blue guy, and so on and so forth, okay? So the size of the angle is giving you the amount of phase shift. A negative phase shift indicates delay or shifting to the right. Positive phase angle indicates advancement or a shift to the left. Okay. All right, so any questions about these basic properties of the sinusoid before we move on to different things? Yes, ma'am. It's both. So it's just a generic angle. So if I look at this guy, so I wrote phi here and theta here because I wanted to be clear that these are going to represent two very different angles, right? So for instance, if we look at this guy as a cosine function, our phase angle theta would be negative, okay? So it might be negative 30 degrees, okay? Well, our phase angle phi for our sine function is very obviously positive because we've shifted our signal to the left. So that's going to be something like positive 60 degrees. So that's why I gave them different symbols, because they represent different numbers. So for what it's worth, if we were calculating this as the phase angle for a cosine function, our delta t would be this amount right here. If we were calculating it for a sine function, our delta t would be this amount right here. Absolutely. So it just depends on whether we're shifting to the left or the right as to whether or not we include a positive sign or a negative sign when we're calculating that phase angle. Any other questions about this? Phase angle, like I said, is probably the most confusing thing, and we're only going to make it a little weirder here in the next couple of minutes. All right, so at times, we are going to need to compare sinusoidal signals. So when we compare sinusoidal signals, there are three basic rules that we have to abide by in order for our comparison to make any real sense, okay? So the first rule is that all signals must be expressed exclusively as cosine functions or sine functions, okay? So let me explain exactly what I mean by that. Let's say that I have some signal, x1 of t, and this is 8 cosine 4t plus 12 degrees. And I have some signal x2 is equal to 5 sine 4t plus 64 degrees. I can't compare these signals unless I convert that sine function into a cosine function, or I could convert that cosine function into a sine function, okay? So in order to facilitate this changing from sine to cosine or cosine to sine, I want to introduce to you guys two trig identities that you might be able to use, okay? So let's just call this trig identity 1, okay? So I can say that in order for me to go from sine to cosine, so let's say that I have sine of omega t plus some phase angle phi. That is the same thing as cosine of omega t plus some phase angle phi minus 90 degrees. Or in a more succinct form, to go from sine to cosine, we subtract 90 degrees from our phase angle. To go the other direction, so let's say that we had cosine omega t plus theta. This would be the same as sine omega t plus theta plus 90 degrees. Now, in electrical engineering, we always use cosine as our basis, okay? The reason why we use cosine as our basis is because cosine, as we talked about in our last class meeting dealing with complex numbers, represents the real part of a complex signal, right? So the real part of a complex number expressed in polar form or exponential form was the magnitude of that complex number cosine the phase angle, okay? So we're going to use cosine as our basis. So in order for me to compare these two signals, I would simply convert that sine signal into a cosine function. So that would simply be 5 cosine of 4t. And then I would say, all right, so 64 minus 90 is 26, or excuse me, negative 26. And my conversion is done, okay? Doesn't have to be any harder than that whatsoever. And if you would like for me to prove it, I can use that Desmos thing and do this real quick. Okay. So that's not what I wanted to have happen. So we had 4 sine 4x plus 64 times pi over 180. So there's our original signal. (26 times pi over 180). The green curve has completely overlapped the red curve, meaning that those two things have to be identical to each other, right? So if we turn this guy off, our graph just turned red, okay? So converting from sine to cosine is as simple as subtracting 90 degrees from the phase angle, and then going the other way around is just adding 90 degrees. Okay. Oops. Our second rule for comparing sinusoids is that all signals must be expressed with positive amplitudes. Okay. So if I had some third signal, let's call it x3 down here, was negative 10 cosine of 4t minus 115 degrees, I need to figure out a way to convert that into a positive 10 cosine 4t plus some other phase angle. Okay. So I'm going to go ahead and introduce two more trig identities here. So let's call this trig identity 3. So to go from negative sine to positive sine, we are simply going to add or subtract, it literally doesn't matter which, 180 degrees. And for a cosine function, it's going to be the exact same thing. Okay. So negative cosine omega t plus theta is going to be equal to positive cosine omega t plus theta plus or minus 180 degrees. So to convert this signal x3 from negative cosine 4t minus 115 degrees, I could have positive 10 cosine 4t and then negative 115 plus 180 is going to give me, I think, positive 65 degrees if my mental math is correct. So this one should be, I think, fairly obvious, but we'll throw it into Desmos just for the hell of it. So let me get rid of that guy. Let me add another one down here. I want to add an expression. So let's call this y3. We're starting with negative 10 cosine 4x minus 115. So that's that purple curve. And I want to verify that it is the same as 10 cosine 4x plus 65 times pi over 180. And my black curve completely overlaps my purple curve. So just adding 180 will get us there. For what it's worth, subtracting 180 would be the same thing, right? So negative 115 minus 180 would be negative 295, right? So I could change this positive 65 to minus 295, and they overlap each other as well. So it literally does not matter if we choose to add or subtract 180 degrees. It is the exact same thing. we're just going halfway around our unit circle, okay? I typically tend to add or subtract depending on which result is going to give me the answer, the angle that is less than 180 degrees in magnitude. But ultimately, it literally does not matter at all. So I'm going to change this guy to Y3. I'm going to put this guy back at plus 65. And then I'm going to wind up just deleting this guy. So I now have these two signals. The last, let me change my settings here real quick. Actually, I'll do that in a moment. The last thing that I want to do here is put that Y1 signal that we started with. 8, 4t plus 12. I'm going to play with my settings. So let's make the x-axis only go from, let's say, 0 to 5. And let's make our y-axis go from -12 to +12. And we'll circle back around to this. And actually, I want to see my axis. Yeah, there we go. We'll circle back around to this in just a moment. Okay. The last rule that we have regarding sinusoidal signals and comparing them is that all signals must have the same frequency. It does not matter if we're referring to angular frequency or linear frequency, since we know that those quantities are just related to each other by a constant factor of 2 pi. And for what it's worth, there is literally no trig identity to fix this. So your sinusoidal signal is either of the same frequency as the one that you're trying to compare it to, or it isn't, and you cannot make a comparison. Okay. So one of the comparisons that we do is determining whether a signal is leading or lagging the other one, okay? So a signal is considered leading another signal if it hits its peak value at an earlier point in time. So if we look back at that Desmos graph, and we're looking at these groups of 3 signals here, I would say that my black signal is leading my red signal, and it is also leading my green signal, because the black signal hits its peak at an earlier point in time than the other 2 signals do, right? So we're comparing the peaks that are the closest to each other, and we can see that it goes black, then red, then green, and it'll always be like that forever because all of these guys are oscillating at the exact same angular frequency, okay? So what does this really mean? Well, it just means that the signal in black has a more positive phase angle than the signals that it is being compared to. A signal is considered lagging another signal if it hits its peak at a later point in time. And this corresponds to the signal's phase angle. Is more negative. So if we go back to that Desmos plot, we could say that the green signal lags the red signal and it lags the black signal because it's hitting its peak latest in time. So we could also say that the red signal leads the green signal, but it lags the black signal because it's in between, okay? Now, quantifying how much one signal leads another or lags another in the time domain like this can be rather tedious, okay? So instead, what we tend to do is we take a snapshot of these signals at a specific instant in time. And usually that specific instant is just t is equal to 0, so that we get to throw away essentially everything but the magnitude and the phase angle of the signal, okay? So let's call these phasor diagrams. Goodness, I can't spell. So I'm going to take those three signals. Let's see. What color should we have here on the Desmos thing? Red for Y1, green for Y2, black for Y3. Okay. So red, green, black. So I'm just going to remind you guys that X1 was 8 cosine 4t plus 12 degrees. X2 was 5 cosine 4t minus 26 degrees. And X3 was 10 cosine 4t plus 65 degrees. Like so. So I could represent those guys on a phasor diagram by something like this. Where this corresponds to 0 degrees, here's 90, here's plus or minus 180, and down here is negative 90 degrees. Okay. So I could say that X1 has a length of 8 and a phase angle of positive 12. So it would be somewhere in this ballpark. So let's just call this X1 of t. X2 has a length of 5 and a phase angle of negative 26. So it might be something like this. And X3 has a length of 10 and an angle of 65. So it might be somewhere up here. like so. So we could use a diagram like this to figure out by how much one signal leads or lags another signal, okay? And so I want to explain what that process is to you guys. So Teresa, pick X1, X2, or X3. X2, okay? So let's say by how much does X2, Cody, pick lead or lag? Lead. And let's see, Caitlin, pick X1 or X3. Just completely arbitrary. X3. So by how much does X2 lead X3? Okay. So let's talk about how we use a phasor diagram to answer this question, okay? So X3 is our reference signal, okay? So that's where we're going to start our measurement from, and we are just going to keep on going until we hit X2. So when we're measuring leading, what we're looking for is a more positive phase angle. So we're going to have to go around our phasor diagram in a counterclockwise direction, okay? So I would start measuring from X3, and I'd go this way for leading, and I keep going until I hit X2, like so. So this portion right here is just 90 minus 65 degrees is 25 degrees. Then I have 90 degrees from this part, 90 degrees from this part. And then here I have 90 minus 26, which would be 74, if my mental math is correct. And I would just add all those guys together, right? So 25 degrees plus 90 degrees plus 90 degrees plus 74 degrees comes out to be, it's 64? Sorry. 269 degrees. So let's do another question. Trevor, pick X1, X2, or X3. X3. Okay. Mason, pick X1 or X2. X1. So if we want to find out by how much X3 lags X1, we would start measuring from X1. So whichever signal is the second one is the one that we're making the comparison to. And in this case, we would actually wind up measuring in the clockwise direction because we're looking for a more negative phase angle, okay? So we would start here and keep going until we hit thank you. Start here. Thank you for that. And keep going until we hit the one that we're interested in, right? So we would have, let's see, so this is 12 degrees, and then we've got 90, 90, 90, and this guy right here is 25. So 12 degrees plus 3 times 90 is 270 degrees, plus another 25 degrees. Comes out to be 307 degrees. So just to recap, The second signal is always the one where we start our measurement. If we're measuring leading, we go clockwise, counterclockwise. If we're measuring lagging, we go clockwise. So leading, we're looking for a more positive angle. Clockwise, we're looking for a more negative angle. Now, you guys have some homework problems related to this concept. I am telling you very explicitly right now that web work is an asshole. You're all aware of it, but I'm telling you explicitly, okay? So what I mean by that very, very specifically is that if you follow this process, which is 100% correct, web work might tell you that you got the wrong answer, okay? The reason why web work might tell you that you got the wrong answer is because web work isn't set up to understand the equivalence between two angles, right? So it doesn't treat 0 degrees and 360 degrees and negative 360 degrees and 720 degrees and so on and so forth as the exact same thing. So if you follow this process and it tells you that your answer is wrong, try adding 360 degrees and checking it again. If it tells you that's wrong, subtract 360 degrees from your original. One of those three will be correct. So you're doing it right. It's just web work isn't set up in a way to know that angles are equivalent to each other. Brendan. It depends on how it was coded and how your random numbers were generated. So you will either get it right just from the jump or just add 360 or subtract 360. I haven't been able to figure out any rhyme nor reason. Okay. Any other questions about this stuff right here? Okay, so I want to get into some circuit analysis now. Normally, I would spend a solid 30 minutes just working one problem, but we're a bit behind. So I'm going to get some help from Desmos and all of this kind of stuff and try to explain things along the way without bogging you guys down too much in trig and all that kind of horrible calculus and stuff like that. Okay. So I want us to analyze what I believe is a very simple circuit. Okay. So I have some time varying current source. Connected in series to, let's say this is a 5 ohm resistor and a 2 Henry inductor. And my ultimate goal is to simply figure out what the voltage drop across my current source is. Okay. So we only have 3 elements here. Okay. So let's say that IS of t is something simple, like 1 cosine 2t plus 10 degrees amps. Now, because I'm pressed for time, I'm not going to go through a big, long explanation of why I expect my voltage across my current source to be of this form, but we can logic our way through it pretty quickly, right? So I'm expecting to see some voltage that will have a magnitude, it will oscillate at the same frequency, and it will probably have a different phase angle than our current. Okay. So essentially, if I put a sinusoidal signal in, it seems fairly reasonable that my response or the output of this system should also be a sinusoidal signal. Okay. Where, depending on what components are connected, the magnitudes of those sinusoidal signals may be different, and the phase angles of those sinusoidal signals may be different. Okay, so think about it in this way. Whenever we had a DC circuit and it was at steady state, if I had DC voltage and current sources, I got an output of DC voltages and DC currents. So it stands to reason that if I have an AC system that is at what I'm going to call sinusoidal steady state, if I put a cosine function in, I'm going to get a cosine function out. That's that's the only assumption that we're making here. So in order for us to analyze this circuit in the time domain, I am going to use Kirchhoff's voltage law. And I'm just going to say that the voltage drop across my current source is going to be the sum of the voltage drop across my resistor plus the voltage drop across my inductor. Okay. So let's say that the voltage drop across our resistor is this voltage VR of t like so, and this voltage VL of t like so that I can say VR of t, excuse me, Vs of t is equal to VR plus VL. So before I go any further from this, does anybody have any problem with that? Nobody saying anything? So let's figure out what those guys are. So I have a resistor, and I have a known amount of current flowing through the resistor. So if I want to find the voltage drop across that resistor, I'm going to just use Ohm's law, because why wouldn't I, right? So that's just going to be R times IS. So that's going to be 5 ohms times 1 cosine 2t plus 10 degrees amps is going to give me 5 times 1 is 5. So I will have 5 cosine 2t plus 10 degrees volts. Does anybody have any problem with that? To find the voltage drop across my inductor, I'm going to use the relationship V is equal to L times the derivative of my current. So my inductor has a value of 2 henries. And now I'm just taking the derivative of cosine of 2t plus 10 degrees. So what's the derivative of cosine? Negative sine, right? So I'm going to have negative 2 because I'm doing the chain rule. So it's cosine of the derivative of the, or excuse me, I'm pulling the 2 out because I'm using the chain rule. So that's going to be 2, and that's going to have units for what it's worth of radians per second. Now I'm going to have sine of 2t plus 10 degrees. Sorry, and that should have been in amps. And so let's see, I'm going to have 2 times 2 is 4. So that's going to look like negative 4 sine 2t plus 10 degrees volts. So if I add these two guys together, I would have 5 cosine 2t plus 10 degrees minus 4 sine 2t plus 10 degrees volts. There's nothing technically wrong with this result. However, it doesn't look like what I would expect it to, because I am expecting my answer to be a single sinusoid, okay? So I want to throw these two different parts here into Desmos really quickly. What's up?
Do you convert the negative 4 sine to the plus 10 into a positive?
We'll get to that in a minute. So 5 cosine 2t plus 10 degrees. All right, so let me get rid of all of this stuff. And then let me just refresh. So let's call VR is 5 cosine 2x plus 10 degrees. And once again, I'm just going to multiply by pi over 180 so that my angles come out okay. And I'm going to say that VL of x okay, I'm going to do V1 and 2 because it's not liking what I was trying to do with letters and subscripts. So this guy was -4 sine 2x plus 10 times pi over 180. Okay, so I have those two signals. And then over here, I'm just going to do V1 plus V2. And if I turn off V1 and V2, just so that it's not as busy, I don't know about you guys, but to me, this looks exactly like a single sinusoidal signal. So there must be some way to take those two results and manipulate them in order to get a single sinusoid out of it, okay? Now, the long way of doing this is a ridiculous amount of trig. And if you want to see me suffer through that, go look at literally any other class meeting number, I think this is 21 or maybe 22, video from previous years of or quarters of circuits 1 or whatever. But because we're pressed from time, I'm going to skip to the easy way and not make you guys watch me struggle with trig for 20 damn minutes here, okay? So what we could do instead of doing just a mountain of trig is something very similar to what was suggested a moment ago, okay? So I'm going to just convert this part right here into a positive cosine function, okay? So to go from negative sine to positive sine, I would add 180 degrees, right? So that would look like plus 4 sine 2t plus 190. And then to go from sine to cosine, I would then subtract 90 degrees. And so I can say that this part in green is just going to look like plus 4 cosine of 2t plus 100 degrees. So is everybody okay with how I went from -4 sine 2t plus 10 to +4 cosine 2t plus 100? Okay. Now, again, ignoring tons and tons of difficult math, I want us to just make a pretty simple observation here, okay? So each of these sinusoidal signals has a magnitude, a frequency, and a phase angle. Well, turns out that an exponential form complex number can also contain a magnitude, a frequency, and a phase angle. So what I'm going to do instead of trying to add these numbers up here as trig functions, I'm going to add them as complex numbers, okay? So essentially, I'm going to say that Vs of t is, I don't know, maybe equal to 5 e to the j 2t plus 10 degrees plus 4 e to the j 2t plus 100 degrees volts. But I can't put this in my calculator like this. So instead, I'm going to use polar form. And remember that polar form is just a shorthand notation for exponential form, where we only keep the magnitude and the phase angle, okay? So this to me would look like 5 with an angle of 10 degrees. And this guy over here looks like 4 with an angle of 100 degrees. And I'm literally just going to throw that into my calculator. So 5 angle 10 plus 4 angle 100 gives me 6.403 and some change with an angle of 48.6598. So let's call that 660 degrees. You didn't get that number? Is your calculator in radians? Is your calculator giving you the answer in rectangular form? So in rectangular form, for what it's worth, and I mean, there's a distinct possibility that I've made a mistake, but I think this will sort out things. So in rectangular form, this looks like 4.229 and some change plus J 4.807. And both of these would be measured in volts. Teresa, is that what you got? Okay. So what I'm going to do now is I'm going to take this guy and I'm just going to kind of work backwards, meaning that I'm going to put it back in that polar form. And then from here, I'm just going to put it back as a cosine function. And I want to see what happens in Desmos. So I'm going to add another thing down here. And I'm just going to put in 6.403 cosine 2x plus 48.660. Thank you. And I'll be damned if that purple curve doesn't perfectly overlap that green curve. Yes, sir.
So that 2T was different, breaks the third rule, what we established earlier, and we compare.
it's impossible for the 2T to be different in a circuit like this. So what I mean by that specifically is if I sinusoidally excite a system at one particular angular frequency, all of my responses will have that exact same angular frequency once I hit steady state. So we just used complex numbers to legit avoid 20+ minutes of trick. Okay. Now, for your homework's sake, I want to show you something here. Because you have some problems that you have to do on your homework that ask you to do similar manipulation to what we just did here. So combining sinusoidal signals and all of that kind of stuff. And the expectation, as far as I know, from when it was written, was to actually make you suffer through those trig identities. I didn't even introduce you to the trig identities because it's a waste of your time, okay? So we can go from any two sinusoidal signals added together to a single sinusoidal signal by converting both signals to cosine functions and then just converting them into a polar form complex number and then doing whatever math we need. But sometimes your homework asks you to express that combination of signals as something cosine omega t plus something sine omega t, where you don't have any phase angles whatsoever to deal with. That's where this rectangular form comes in, okay? So for what it's worth, this guy right here actually represents 4.229 cosine of 2x minus 4.807 sine 2x. Okay, I want you to notice that a plus sign on the imaginary part winds up giving you a minus sign when you have it expressed as a combination of a cosine function plus a sine function, okay? That actually comes from one of those trig identities that I'm skipping showing you today because it's not really worth your time. But we can prove it here really quickly just to assuage your fears or whatever. Okay. So as a third thing, let's do 4.229 cosine 2x minus 4.807 sine 2x. And this is in black. And that black curve has completely overwritten our purple curve, which again has completely overwritten that green curve. So all three of these things are literally the same damn thing, just expressed in different ways. So you can actually avoid doing essentially any trig identities in this class, except for converting from sine to cosine means subtract 90 degrees. Getting rid of a negative sign means adding plus or minus 180 degrees. Everything else can be handled by complex numbers. So we've worked this example problem, and what did you guys think about this? So fairly straightforward, but it was also a lot. So it would be damn convenient if there was an easier way to do this, wouldn't it? So let's talk about that even easier way to do this. So instead of working things in the time domain, let's talk about how things work in the frequency domain, okay? So let's call this Introduction to Frequency Domain Circuit Analysis. That is a G. All right. So we are, for lack of a better word, exploiting one particular trig identity when we're doing this. So I'm going to go ahead and give you guys that trig identity because I feel like it's so important. You won't ever have to use it directly. And technically speaking, we've already kind of been introduced to it, okay? So the trig identity that I'm referring to is a thing called Euler's identity, okay? Euler was I believe he was a German mathematician who wound up living in Russia for the overwhelming majority of his life. He died effectively penniless, which blows my mind because without his work, the field of electrical engineering as we know it could not exist, okay? So this is a very, very important dude. And he came up with a couple of different relationships. The one that we're going to talk about today is this guy, okay? So what Euler found was that if I have the exponential of e to the j omega t plus some phase angle theta, that is the same thing as cosine omega t plus theta plus j sine omega t plus theta. That is literally just how we convert from exponential form into a rectangular form complex number. So you guys are actually already familiar with this because these are the ways that we went back and forth with it in our last class week. So let's see how this applies to electrical engineering in particular, okay? So let's say that I have a voltage signal, V of t, is equal to Vm cosine omega t plus theta v. Okay? This is my generic time domain voltage. And I'm going to have some generic time domain current signal as well. I am cosine omega t plus theta I. Well, we can recognize these signals as simply the real part of the following complex numbers. Vm e to the j omega t plus theta v. And here is Im, excuse me, the imaginary part of Im e to the j omega t plus theta I. I'm going to call these guys mixed domain signals. I'm calling them mixed domain signals because they have both time components and frequency components. Okay? And what we can do is we can use that shorthand notation, just like we did a couple of minutes ago, where we just keep our magnitude and we keep our phase angle and we throw everything else away and come up with what are called phasors or frequency domain signals. So this V with a bar over it is my phasor voltage. Okay, so it's how I'm going to represent voltages in the frequency domain. And all I'm going to do is I'm going to take the magnitude, I'm going to take the phase angle, and I'm just throwing everything else away. So realistically, we don't even need that intermediate step, right? Because our sinusoidal signal expressed as a cosine function has a magnitude and it has a phase angle. So I can go directly from the time domain to the frequency domain by just keeping my magnitude, keeping my phase angle, and not worrying about anything else. And I can do the exact same thing for my phasor current I. So that's going to look like Im angle theta I. Okay. The only thing we really need to worry about is if we aren't given a cosine function. If we're given a sine instead, we simply just subtract 90 degrees and then treat it like a cosine function, okay? So as a quick example here, bless you. So let's say that I have some signal V1 of t is equal to 14 cosine 35t plus 106 degrees. What would my phasor voltage V1 be? What? 14 angle 106. I literally keep my magnitude, keep my phase angle, throw the rest away. Don't have to do anything else. What if I had V2 was 7 sine 5 pi plus 94 degrees? Do I add 90 to go from sine to cosine? I subtract. So V2 would just be 7 angle 4 degrees because sine, 5 pi plus 94 is the same thing as cosine 5 pi plus 4 degrees. That's it. That's the trick. So just be on the lookout for being given a sine function every now and then. Whenever you see sine, subtract 90 degrees. Carter. That's just, that should be 5 pi t. Okay. So how comfortable do you guys feel with converting from time domain signals to phasors? Pretty straightforward, right? All right, so what we're going to look at now is frequency domain relationships for current, excuse me, for resistance, capacitance. What's up, Ty? Yeah, I can't do it until after I'm done giving a lecture. Yep. It's one I already did it, whatever. Resistors, capacitors, and inductors. Okay. So let's say that I have a resistor. Where the voltage drop across my resistor is this V of t, and the current flowing through my resistor is this I of t. And we know that V of t is a sinusoidal signal. So let's just say Vm cosine omega t plus theta v, which is again just the real part of Vm e to the j omega t plus theta v. And similarly, our current I of t is Im cosine omega t plus theta I, which is just the real part of Im e to the j omega t plus theta I. So I know that the voltage drop across my resistor is simply going to be R times the current flowing through my resistor. Yes, Brianna. So I'm simply going to substitute in here, but I'm going to substitute using that complex representation there. So I could say that on the left-hand side, I would have Vm e to the j omega t plus theta v is equal to R times Im e to the j omega t plus theta I. And what I'm going to do now is I'm just going to split those exponentials into more digestible pieces, right? So I could see that on the left, I would have Vm e to the j omega t times e to the j theta v will be equal to R times Im e to the j omega t times e to the j theta I. And there's a common factor of e to the j omega t on both sides of the equal sign. So I can just throw it away, which explains kind of why I've been able to throw it away, or I've been throwing it away this entire time, okay? It's always going to wind up canceling out. So that leaves me with Vm e to the j theta v is equal to R times Im e to the j theta I. So let's take a moment to look at this. Essentially, what I have is an exponential form complex number on the left-hand side of the equal sign and an exponential form complex number on the right-hand side of the equal sign. So that means that the magnitudes on the left have to be equal to the magnitude on the right, and the phase angle on the left has to be equal to the phase angle on the right. So I can just look at this guy and I can say that Vm is equal to R times Im, and I can say that theta v has to be equal to theta I. So essentially, a resistor does not introduce any phase shift between my voltage and current. So if theta v is equal to theta I, then those signals perfectly align with each other in both time and frequency. Okay. Well, these exponential form complex numbers here could be written as polar form complex numbers. So that would be Vm angle theta v is equal to R times Im angle theta I, and recognizing that Vm angle theta v is nothing more than phasor voltage V, and Im angle theta I is nothing more than phasor current I get Ohm's law in the frequency domain. Phasor voltage V is equal to or phasor current I times R. So Ohm's law is still just Ohm's law, but now we're using complex numbers. I'll give you guys a moment to continue to catch up here, and then we'll talk about capacitors and inductors. All right, so let's say that I have an inductor. I'm going to use those same voltages and currents from before. So we have sinusoidal signals, right? So I know that the voltage drop across an inductor is equal to L times the derivative of the current flowing through my inductor. And so, excuse me, when I substitute things in, that's going to look like Vm E. Let me go ahead and split this up like I did before. E to the j omega t, e to the j theta v is equal to L times the derivative with respect to time of Im e to the j omega t e to the j theta I, like so. Okay. So Im and e to the j theta I, neither of those depend on time, so I can pull them out of my derivative. So that would look like L times Im times e to the j theta I multiplied by the derivative of e to the j omega t. Well, what's the derivative of e to the j omega t? What was that?
Omega t to the j.
There we go, j omega times e to the j omega t. So I have Vm e to the j omega t e to the j theta v is equal to L times Im times j omega t, j omega e to the j omega t e to the j theta I. And once again, these e to the j omega t terms go away. Now, I have an exponential form complex number on the left-hand side, but I don't quite have an exponential form complex number on the right-hand side, okay? So what I mean by that is, if that factor of j wasn't down there being multiplied by omega, I could make this look like exponential form complex numbers on both sides. So let's take a moment to recognize what that j kind of represents, okay? So I'm going to do that up here to the right. So here I've got a complex plane. Here's my real axis, here's my imaginary axis, and so on and so forth. So if I go out 1 unit in the real direction, we most commonly refer to that as literally just the number 1. Okay? But in rectangular form, that would be 1 plus j0. And in exponential form, that would look like 1 e to the j 0 degrees. Well, if I go up 1 unit in the imaginary direction, we probably call that j, but in rectangular form, we could write that as 0 plus j1. And in exponential form, that would look like 1 e to the j 90 degrees. So essentially, this j right here represents me multiplying by a factor of e to the j 90 degrees. So I can actually pretty this up a little bit, okay? So I could have Vm e to the j theta v is equal to, so let me reorganize some things here really quickly. So one way that I could put this would be j omega L times Im e to the j theta I. But another way that I could write this would be omega L times Im e to the j theta I plus 90 degrees. So from these relationships, I can see that the magnitude of my voltage, Vm, is equal to just omega L times Im, and I can see that the phase angle of my voltage is going to be equal to the phase angle of my current plus 90 degrees. So what we've just stumbled into is that the phase angle for our voltage will always be 90 degrees more positive than the phase angle of our current. Another way to think about that is that our current is always lagging our voltage by exactly 90 degrees in a pure inductor. So now let's put things in terms of phasors, right? So Vm e to the j theta v is the same thing as Vm angle theta v. And here I've got j omega L times Im e to the j theta I. So that's j omega L times Im angle theta I. And thus I get phasor voltage V is equal to j omega L times phasor current I. The derivation for a capacitor is going to be incredibly similar because we know that capacitors and inductors are just the electrical duals of each other. So I'm going to skip a number of steps with this derivation, okay? So for a capacitor, we know that I is equal to C dV by dt, right? This is practically the same damn thing we just had for inductors, except that V and I have swapped places, and instead of having L's, we now have C. So jumping ahead several steps, this would look like Im e to the j theta I is equal to j omega c times Vm e to the j theta v, or omega c times Vm e to the j theta v plus 90 degrees, which means we could say that the magnitude of our current is equal to omega c times the magnitude of our voltage, and we can say that theta I is equal to theta v plus 90 degrees, meaning that our current leads our voltage by 90 degrees whenever we have a capacitor. So the current phase angle is always 90 degrees more positive than the voltage's phase angle. Okay. Using polar form, this looks like theta I is equal to j omega c times Vm angle theta v. And in terms of our phasors, then we have I is equal to j omega c multiplied by phasor voltage v. All right, I have been talking for roughly an hour and 40 minutes straight. So there's actually more stuff that I want to cover today, but we'll push it off until our next class meeting. Don't worry about the ICA for today, unless you guys just particularly want to spend 10 minutes looking at it. But realistically, you could only do problems 1 and 2 anyway right now. So, yeah. All right, we'll pick up on Wednesday by starting with what's called impedance, and then we'll go on from there. Brendan, how may I help you?